Okay, folks, it's 8:30. Good morning. Can somebody tell me whether you can hear me or not, please?
We can hear you.
Okay, thank you. Thank you. All right. So today is the wrap-up section on beam elements. Although I did mention that I'm pretty much done the other day, but in the course syllabus I put down today as the catch-up day. So there's a few items that I want to do, and basically it's a review. There's nothing new. However, it's very helpful. So there's a situation. It very frequently after I do beams and shells, some people will say, "Oh, wait a minute. We could have done this thing with solid elements without any hassle, and I could have got results." Well, although that statement is true on its face value, it is not true when it comes to actually being able to do it properly. As I said, if you have, for example, the hood of a car and you put some weight on it, it's hinged at some point, you weight on it, you sit on it, whatever, and if you want to find the deflection and the stresses in the hood so that it doesn't permanently deform, you might say that, well, I'm going to model this thickness of about 2 millimeters probably of steel or aluminum, whatever the hood is made of, using solid elements, whereas you know that the dimensions of the hood are about 4 feet by 3 feet or something like that, and then the thickness is only 2 millimeters. Now try to put those solid elements through the thickness of 2 millimeters when the whole thing is 4 or 5 feet. Okay, and you're going to end up with so many elements that for all practical purposes becomes impossible to do using a regular computer. Same with the beam. I mean, look, if you want to open a can of soup, you can use any one of these. However, it's going to be very messy to do it with a hammer or a knife. So you need the proper tool to do what you want to achieve. Not that these cannot be done, but just imagine. Here's the other example that I'm going to show you is that I just talked about the hood of a car. Look right there. This is about maybe 4 feet, 5 feet, 6 feet this way. Thickness about, I don't know, 2 millimeter, quarter of an inch. Now imagine trying to put these solid elements through the thickness, few of them, and then cover that entire area. Well, you're gonna end up with I don't know, maybe 200,000 elements in this, whereas you can do it very efficiently with covering the surface with shell elements. In shell elements, you just cover the surface topology and then tell the software, for example, what is the thickness of the shell. If you have a bulky object, and even this can be done with shell to some extent, well, you're going to try to cover it with solid elements. If you have a frame structure of a building or a minibar, Formula One, why you're not going to model these things with solids. You're not going to model it with shells, okay? Because these flanges are very tiny, etc. So imagine trying to put, for example, solid elements through the thickness here, or shell through this big area all the way from one end of the building to the other. So you model this thing with beam elements, okay? Now, don't be fooled though. Don't be fooled. If you want detailed stress distribution at the juncture where these things are coming together, etc., you have to go to solids, okay? This beam is going to give you excellent result for deflection, for natural frequencies, for specific type of stresses, for software that will do it for you. Not in CATIA though. CATIA will not do stresses for you in beams, okay? But there are other software which you give it some minimal instructions as where to calculate the stress in the beam, and it'll do it for you. Because remember, in solids you can say, and go plot the stress everywhere. Or in shell, you say that go and plot the stress everywhere. It'll do it for you. But when it comes to beams, you cannot say, what is the stress in the beam? Well, the question is, where in the beam? Because the beam stress varies through the cross-section, point by point, okay? And some of the software may have set excuse me, default locations, or they may accept instruction from you or where to display the beam, etc., and they'll do it for you, but not CATIA. Okay. Now, when it comes to beams, there are two approaches. One is if your structure, such as this ring, for example, such as this, I don't know, this frame, if they can be drawn or they can fit, let me put it this way, in a sketch, in a two-dimensional plane, then what you can do, you can very easily create these sketches and then proceed from that point on. And you take it into 3D space, of course, that's still sketch, okay, but it's in two dimensions, it's in a plane. And then you go from that point on, you join it and mesh it, blah, blah, blah. On the other hand, there may be beam structures that do not fit in a single plane. If that is the case, either you draw it in space completely, this is not a sketch, or a combination of, for example, sketches. If you look at the spring, there's nothing you can do. You just have to draw it in space somehow. And don't look at this thing as solid element, solid object. We got I drew it for you so that you can see it. But this is actually a helix wound up, just a curve in space, a helix. Or here, you can do it as 3 sketches. One this sketch, one this sketch, and one that sketch. You can go that route too, okay? But here it's impossible. You have to draw it as a wireframe in 3D space. Now, look, these are going to come on the test. You're going to have to remember the conversation that we had. When you see this, every problem says use the most appropriate element. You should not go and model this or that or that. Here also true, but it's kind of becomes iffy. In other words, if you want stresses, then obviously you can't use beams. And if you want stresses for springs like that, then you have to do it with solid elements. But if that is not the case, you should do these things with beam element. There is a major point deduction if you try to do these things with solid elements. Okay? All right. And the whole idea of we working together, coming to class, going, you know, doing homework, etc., to be trained, to train our eyes, so that when we see something like this or like that or that in 3D, we don't just jump on CATIA and draw a line and say parrot or ribbit or, you know, etc. Okay, so this bottom one, the one at the bottom right corner, is actually the one I want to do today, and it's coming from some of the old tests that we had a few years ago. Okay. Same thing with this. These two have seen it in your homework. And if they did not appear in your homework that you're uploading this week, okay, today is your lab, this is lab 54. I don't know. You may not have had these two problems. Well, check the other section's problems, okay? They had something like that. Okay, you may have had something else. I'm not sure. Okay. So the problem that we're gonna do is right here, and all it says is that, look, these two ends are clamped. These two ends are clamped. And you're given cross-section of these two, these pieces. Okay, they're different. You can look at it. We exaggerate it so that you see, unless you have a really bad eyesight, and I do, that this cross-section is different from this cross-section. Okay? So then the loading is that you apply a force here. You apply a force. We don't know what the value of the force is. It's something that you can ask CATIA to give it to you at the end, which gives you 0.001, a thousandth of an inch displacement, and a moment here, which you don't know what it is, so that it twisted by 2 degrees. Okay? So you have to apply a force here to pull this. You have to apply a moment here to twist this thing by 2 degrees. Okay? Now look, use all planes of symmetry if applicable, and use the most appropriate element. Now, the most appropriate element, we already see that it has to be beam. There's no ifs and buts. Okay? As far as the symmetry goes, these things, okay, you do problem, you watch me, you watch your friends, everybody, you get the hang of it. Just common sense. Just pretend this moment is gone. Don't worry about this moment. You have the structure like that. Hopefully this is right at the midpoint. Yeah, it is. If not, always ask, okay? And you're pulling it. Do you not agree that the deflections all the on the top and the deflections on the bottom are the same? I hope you see that. Now, think about the moment the force is gone. Forget about the force. You twist this thing right at that location somehow. Somehow you twist this thing. Somehow you twist this thing at that mid location by some amount. Okay, with supply. Do you not agree the top and the bottom are the same? Now, the geometries must be the same. The dimensions must be the same, and the nature of the loading must be the same. For example, if I took this force and instead of applying in the x direction, let's say I applied in the y direction or z direction, all bets are off. There is no symmetry. The geometry is still the same, but the loading makes it unsymmetric. Or if one top point is clamped, the bottom is not clamped. There's no plane of symmetry. Okay, so let me see what I have here. Oh, in this particular problem, because I didn't want people to make, it's kind of ugly if I just, unless I give it like that, it becomes ugly. Okay, so I'm saying that, hey, look, here's the detailed geometry from the close-up, okay? And the radii are given here, and the coordinates of these things are given. It's entirely up to you how you want to make that geometry by giving these things, and hopefully I didn't make a mistake in the coordinates, and if I did, it's going to show up when you do it. You can create this wireframe in space and proceed from that point on. Okay. Well, before we do the problem, are there any questions? Okay, a couple of things. These presentations that and in the lecture and the lab, of course, I'm reporting, not reporting, I'm recording it, and it's going to be available for you on Blackboard. But I have also downloaded those videos that are available to you on Blackboard and edited them. When I say edited, I maybe censor some stuff that I might say, or some comments that people might make, and it may show up on the right side, okay, and and posted them on YouTube, so that who knows, maybe there is somebody else in, I'm not sure, Namibia who wants to learn about this. All right, good. So let's go ahead, and there are no questions, so let's go to Katia. And you got my email last night. From this week on, the GAs are going to be very strict about making those deductions in case documents are not properly submitted or not submitted at all. So let's start with the part file. Okay. And immediately we save it. File, save management, save as, desktop, new folder, and I will call it, today is lab, this is lab 54, May 25. Okay. And the name of the file, remember, that's how you name them, upload them as an assignment, and later on in your test. Your student ID number, 123456789. Your last name, I think this week you're Bernoulli. This is, I'll say problem 1, because I may do it with a sketch also. This problem I may do it with a sketch, I don't know. Problem 1, and it's going to be with wireframe. Okay. You say okay, and you say okay. All right, so you create these coordinates. You create these points by these coordinates. My units are inches, and I have decided on the midterm, I will give you only imperial units. So if you want to set up your units ahead of time so that it's inches and pounds and PSI and things like that, by all means, go ahead. I'm not going to mix it up. Points. Now, we can create points and lines and stuff like that in part design. There's no problem. But curves in space, such as circles and things like that, you can't do it here. You can see that. So let me do, just so that remind you it can be done here. I'm going to create all my points here and the line, but the curves cannot do here. Okay. So we go to point. Let me start with point. It really doesn't matter. Once I create them, I know what is what. So 0, 0, 10. Supposedly that's point A. And it's going to be 005. Then it's going to be 505. And then 50 minus 5. 00 minus 5. So that's going to be 00 minus 5. And 00 minus 10. This is done, so cancel. Let's look at it, make sure we got all our points. Yep. Yeah. Okay, so let's do our lines first. Line, I can do it here, no problem. From this point to that point. Okay. All right. From this point to this point. Okay. From this point to this point. And from here to here. Okay. Cancel. Now I need a circle in the, let's see now, in the YZ plane, right? In the YZ plane. So there are different ways of doing this thing. I want to know what would be my favorite way of doing it. Okay, so here's the way I'm going to do that. You see, this circle lies in something parallel, a plane parallel to the YZ plane. Okay, and offset by 10 inches. Look, there are different ways of doing it. This is how I'm going to do that. You may come up with a much smarter way of doing it. No problem. So let me first create a plane offset from this plane by 10 inches. Actually, by 5 inches. I wanted 5 inches, so it's not that. 5 inches. Okay, good. Now I want to draw a circle here that passes through this point and passes through that point. Okay, so actually let me do the following. Maybe it's easier if I also created a point here, which I'm going to use at the center of that circle. Okay, so I'm going to create a point, and that will be let me see, 5. Is it 5? I think so. No. Cancel. Okay. You know what? The easiest thing to do is create a point between. How about between this point and that point? That's easier. Halfway. Okay, good. I can use this as a circle, as a center. Now, I want to do a circle here. You cannot do it in part design. There is no stuff like that. There's line and point. So you go to wireframe and surface design. You go to generative shape design. Generative shape design right there. I keep referring to wireframe and surface design because there is a way of doing it in part design, as long as you're willing to go to that particular unit. No, don't worry about it. Here, where's the circle? There's a circle. What about doing get center, support, and radius? How about doing it like that? So the center is here. The support is the plane that I created. And the radius is, I think it's 5, isn't it? Okay, it's just the angle we have to fix. So let's go 90 to 270. I hate this. That's good. That's good. All right, good. So save. Now, those of you who may be looking at some of the older videos from the past few years, or you may, well, this problem is not done in the book, but one problem that's done in the book, maybe, you see that I'm doing it different from what I'm showing you today. And notice that in my slide, I said here, look, oh, I didn't say it there. I thought I had a, oh, there it is. Yeah, right here. Okay. Now I'm trying to avoid two concepts which were done in the previous years. One is I want to avoid this connection, something called connection, and I'll talk about it in a minute. And I don't want to take you to advanced meshing tools as much as I can help. Okay. So how am I going to do this thing? I created the wireframe. Okay, created the wireframe. I joined it. When you join and you try to put a cross section on it, it's going to put it everywhere. All of them are going to have the same cross section. So if I just did the join and put a 1D property on the join, all of these are going to have the same cross section. And this is something I'm going to show you. You can use the local 1D property. After you put a cross section on all of it, then you can do local 1D property to make cross section smaller in some places. This I never did before. That's why I had to appeal to this business of rigid connection in the past, and I'm not going to do it this year. Okay, so join right there. See that? Join. Okay, and this one. Oh, I want to ask you a question. I can do that, but I have a question here. I have two choices. I can make the cut now because I need only half of that, or I could have created this object as half of it to begin with. That's entirely up to you. Okay? So let me do the following. Let me cut this. Okay, let me cut this into two pieces. Where is the cut? Split. We need the split. Let's see now. Where is the split? Oh, there's split. Let's read this thing carefully. It says cutting elements to cut. I want to cut, essentially I want to cut this, right? I don't want to cut these. There's no need to it. Just take it away. Delete it if you want. And the cutting element is this plane, XY plane. Notice that it took that. And we say, okay. Now, these other guys, I can just either delete or later on when I do the meshing, just don't mesh it. As simple as that. I'm not going to delete it. I'll keep it here. How about that? If it's bothering you, you can delete it. Okay. Join this guy, that guy, and that guy. And we say, okay. And apply material on the part. That will include, of course, the join. I don't know, what did I have? I'll make it steel. And say okay. And save. Sometimes you may be shooting in yourself in the foot if you left like things like this, and then you run into problems later on. Yeah, it's up to you. I'll just leave it. Now we're going to go to generative structure analysis. Okay. Static. What's the first thing that I have to do here? Can you help me with that? What is the first thing that I do when I go there? Can somebody tell me? Are you awake? Okay, now you just tell me, because now I have to, if I go there and see what you're saying, who you are, then I have to edit it later and delete it. Can you say it?
Do you have to do the save management?
Yes, that's a good point to save this. Yeah, yeah, and I'm going to do that. I have no problem. But after that, suppose we did that. What's the next thing? Yeah, you're right. What's the next thing that you do?
Beam mesh?
Yes, you have to mesh it. Right. That's correct. Yeah, good. So we have to do this file save management. Since you brought it up, let's do that right now. So file, save management. Here's your analysis. Save as. In that folder, we are in the right. No, we're not in the right folder. Be careful. Be careful. You're not in the right folder. Things like this happen. Where are we? Oh, desktop, right? Desktop, right, left 54. And the analysis, I'm going to give it the same name that I had before up there. Your student ID number 1, 2, 3, 4, 5, 6, 7, 8, 9. Bernoulli. Why don't I call it the same thing? Problem 1. Underscore wireframe. Yeah, part 1. Okay, and that'll be analysis 1, of course. We're fine. And then we say okay. And then we say okay. And now we're going to go mesh it, just like you said, right there. Now, I'm just going to do this. I'm not going to do that. I'm not going to use these. These are just sitting there. If it's bothering you, just hide it. Okay? These points bothering you, hide it. I am going to mesh this join. Now, let me just say a couple of words about this business on me trying to avoid that thing called connection, rigid connection. Now, if I had not joined these, things, I would have to mesh this guy individually, that guy, and that guy. So I have to click on this thing 3 times for this, for that, and for that. And because of that, at the interface here, you have different nodes, one coming from the vertical piece, another one coming from the horizontal piece. And these nodes have different node numbers, and they don't talk to each other. So that business of connection that I was talking about, you create a connection between these two, and you basically say it's rigid. In other words, when one moves, the other one moves with it. But doing it this way, joining it, will avoid getting those duplicate nodes. Okay? Say okay. If you want to see your mesh, no problem. Mesh visualization, say okay. Let's zoom in closely to that corner, for example. Whether you come from the top node, top element, that node is 30, the corner node is 30, or if you come from here, the node is 30. If these were not joined, the node on the top and the node from the side would be different. And this is why you have to create connection. We will see connections, but not for these beams, Okay. Rest of the problem, deactivate that. Very good. You know, these points and things like that, it's a good idea to hide them, because inadvertently you may clamp the point and CATIA will go crazy. Basically, you won't see it. Okay, very good. Now, the next thing that we do is join, is 1D property, right? 1D property. Now, notice that in my drawing, I have, what is that? These have different cross sections. Because I joined it, whatever cross section I put in the wrench, that number that I put in the wrench, it'll take it for the whole thing. And that's not the case. But let me show you how you fix that. So this is 0.4 and this one is 0.15. Okay, so let's pretend that it is actually 0.4, which means everywhere, 0.4, put 0.4 here. And I select this, the whole joint is going to be picked. There we are, you can see that. These are 0.4, this is 0.4, and this is 0.4. But in my case, these two must be 0.15. Now, first of all, notice that because it's circular cylindrical beam, you can close it. You don't need an orientation point. Here is your property that you, what is that? Here's the property that you created right there. You can double click on it if you want. See, this is the one that you created. But if you put the cursor on it, right click at the bottom, it says local 1D property. Local 1D property. You click on it, it says, okay, where are your exceptions? Well, my exception, one of them is here, and I can put a wrench in there and put 0.15. And my other exception is right there, which is the same value, of course, 0.15. Now, if you look close enough, you see that, yes, for this vertical one, it has the big circle, but it also has the small circles at the end, indicating that you're ignoring this. The software is going to ignore that. It's going to use the local value, 0.15, and the same thing here, 0.15, 0.15. It will ignore that. And here, of course, we didn't make any change. This is the original 0.4. Okay? So this makes your job easier. You don't believe how many people screwed this up pre-COVID. Okay. So save it. All right. So let me now do the rest of the problem. Anything that's bothering you, it's blocking your view, you can go hide it. For example, you can put the cursor on properties, right click, hide. Okay, it's cleaner. Okay. This top is fixed, clamped, right? This top is clamped. Good. Now, this point is in the plane of symmetry, and the plane of symmetry XY. Okay, this point is over here. It's in the XY plane of symmetry. As soon as you say XY, Z is 0. Displacement in Z is 0. Displacement in direction 3 is 0. Z3, Z3. Okay. And rotations are opposite. So the first thing I'm going to do is to apply the symmetry restraint. Okay, so go back here. User define that point, and I insist on calling this thing symmetry condition. It's a lot easier if you did it like this. You can easily debug it later on. And we said that that point lies in the XY plane. No displacement in Z. That's easy to see. Rotations opposite. So because this is fixed, this is checked. It should be unchecked here. These are not checked. For rotation, they should be checked. So, okay. Let me just say a few words about this business. When it comes to marking the test, you know, I'm really, unfortunately, it is going to be a case that some things, most things have no part marks. In other words, if you saw the symmetry and you took only half of that, great, you get the mark for the symmetry. But if you made a mistake in your restraints here, you don't get the part marks for the restraints. Because, and please be fair, because how do I know what to do? What if you just checked everything? Okay, just because you know where that thing is, doesn't tell me you understand what's going on. You know you have to do this, but doing this is not good enough. You have to tell me which one. And I mean, you cannot argue that, well, I checked all of them, 3 of them are right, the other 2 are not right. So I get part mark? The answer is no. So I just want to make sure that these are not surprises to you later on. Okay. Now, The next thing is that I'm pulling this in the direction X. Okay, so let's do a user-defined string. Let's uncheck all of these. And I'm going to call pulling in X. How about that? Pulling in X direction, something like that. That point, and if it's bothering you, just hide the stuff that's there in front of your eyes. Just hide this middle one right there. This one, we want to pull it by 0.01, but in order to pull it first, you have to say it's 0. Okay, so direction X 0. And then if you want, I can change it right now, right here. Enforce displacement on this guy. And I can't remember, I think I said point, make sure you read these things carefully, 0.01. Okay, 0.01. Very good. Let me say okay. I also want to twist this thing by 2 degrees. So let me hide this. Once again, user defined. You can see why I'm not putting everything in the same dialog box. It may be possible, but so I'm going to call it twisting. Twisting. Whatever, about 2 degrees, whatever it is. And this is bothering me, so let me, right. Okay, twisting. This is about the z-axis, right? About the z-axis. So rotation about the z-axis first, I want to make it 0, and then I'm going to change it. There. No, about the z. Z is here, right here. Not this. I was looking at this thing. Look. You want to twist it about the z-axis. Okay. By the way, if you say, why am I seeing this red thing? Because that is your load. If you want to hide your load, you won't see that red stuff there. You see that? Okay. And now you can change that. Use enforced displacement of this thing that you just did by 2 degrees. 2 degrees. Okay. Save everything. Because you already saved it properly, all you have to do is to click on that floppy. Okay. And don't forget my advice. Always pray. Because things happen, things go wrong, you have to go fix it if needed. It didn't. Okay, very good. So let's look at the deformation. These beam type stuff, there's nothing exotic about them. I mean, sometimes it's not easy to see what's going on, even if you plotted it. Here, what I did is actually did the displacement, which is easier to see. There we are. And let's put it in a view that we can identify with. So let's put it in the front view first, like that. So looking at the front. So this comes towards you and it twists. Okay, so let's see. Right there. I think that makes sense if you look close by. The fact that it's coming towards you means that does not go up and down. Remember, we fixed the Z displacement because of symmetry. Remember, that's the first thing that we did. No displacement in Z. It doesn't go up and down because this is a plane of symmetry. Exactly the same thing must be happening at the bottom. It cannot go up and down. Because you're twisting it, this thing goes to the right. Now, look, that is, and by the way, here you can see what happens. Because it's twisted, this goes to the right also. And that's why it kind of becomes weird there. If you look at it, it becomes weird, but that's because it goes to the right. Okay, a couple of things. Some software, which have much better capabilities in beams, allow you to draw this thing on the actual cross-section size. That's really useful. You can't do it in CATIA, okay? In other words, it fictitiously changes it to a three-dimensional viewish view, which is not true. I mean, this is just a wireframe. It cannot be three-dimensional. Okay, but that is something helpful that some of the software might have. Not in get yet. Close it. Now let's answer some questions. How much force was needed in order to pull this thing 1/1000th of an inch toward us? Okay, so what we're gonna do, let me deactivate. I don't actually have to deactivate it. Okay, so put the cursor there, right click, internal reaction sensor right there, create resultant sensor, create reaction sensor. If you want to know what those things are, go to some of the videos that I've posted outside of this lectures in the classroom, things like that. Okay, now, so this one, let's see now. Pulling towards us, that was this, right? Or pulling towards us. You click on it. This was pulling towards us. And you update, it tells you that you have 98 pounds multiplied by 2. Don't forget that. 98 multiplied by 2, because this gives you the force needed for that model on the top. We didn't model the bottom piece, so you need just as much for the bottom piece, so multiply this thing by the 2. Don't forget that. We also want to know how much torque is needed to twist that by 2 degrees. So this guy right there. Update. Oops, wait a minute. Oh, moment. There's 2 tabs here. I'm looking at 4th tab. Look. Moment, right there. 520 pound force inch. Don't forget to multiply it by 2. That's how much you need for the top piece. You need the thing for the bottom piece, and you get double of that. Okay, save. Are there any questions? I have 8 minutes, and I want to redo this problem for you using Sketch. Okay, so let's do that. Let me quickly close this. If there are no questions, I'll move on. Okay, I'm assuming no question. If there are any question, ask, please. Part. File, save management, save as. My folder is not right. Desktop, Lab 54, right there. This thing, except that I'm not going to use wireframe, I will use the sketch. PCH. Is there a question?
Do we use wireframe or sketch on the lab?
That's entirely up to you. Entirely up to you. Just get it to work. Okay, so let me do 2 sketches. One is for this piece. I'll do a sketch for this piece, and then I'll do a sketch for a quarter of a circle. Okay, so let me see now. On that vertical plane, I will sketch. Now. I think this was it was something like that. Yeah, I can't remember what. No, gee, how this thing was. Down and to, okay, so come down here. We'll clean it up in a minute. Okay, let's clean this up. So from here to here, I think this is 5. I'm assuming that, yeah, this is what I had. Okay. Yeah, and these, I think these were, if I'm not mistaken, this was 5. Something to that effect. I'll leave it to clear it up if you want yourself, but this is also 5. Okay, exit, So this is this guy. Then on this vertical plane, I will draw. No, on this plane, on the YZ plane, I will sketch that circle, quarter of a circle. So it looked like this. Let's see now. Do it any way you want. A quarter of a circle right there. I can clean it up in a minute. Goes like this. And I have to clean this up. So from here to there, either 0 dimension or make it coincident. It's up to you. There. Definitely that's going to be 5. Exit. Okay. Whoops. Oh, wait. This was the wrong plane. Okay, so here, that's easy to fix. I go there, I cheat. I go there. You know what? Let's clean it up. So let me create a plane. I should have drawn a plane right there. Remember I created a plane? So this sketch, let me delete it. It's easier if you delete it than to fix it. Believe me. Delete. Okay, create a plane, offset from this plane by 5 inches. There are more efficient ways of doing it, but I'd rather not take you there. If you already know, that's great. Okay, so this control that coincident or dimension 0. There we are. That's a lot better. Okay, so you have 2 sketches here. Now, what we can do is we can join each one of them. Okay. Now remember, to avoid that local thingy, to avoid that duplicate nodes, we're going to join both of these sketches. So join this sketch and that sketch, 1 and 3. Very good. Okay, excellent. And apply material to it. Metal, I don't know, steel. Okay, steel on the part. Okay, good. Save. Go to generative structure analysis. You still have 3 minutes, right? Say okay. Mesh it. Because we joined it, the whole thing is going to be done. Those duplicate nodes are not going to come into the picture because we joined it. Now 1D property, we can put it on the join. This was 0.4. Yeah, that's good. And guess what? Now local 1D property on this piece, which we'll put down 0.15, and on that piece, which put down 0.15. Analysis, file, save management, save as, not that, the analysis. Save as, desktop, there we are, except that this is going to be sketch. Okay, basically I use 2 sketches. The rest of the problem is the same, so I'm not going to do that. It's exactly the same. Create restraint, symmetry, create restraint, run it, and then sensors. Okay, so now I have safely created 2 folders here. Where are my folders? Lab 54. I have 2 parts, 2 analysis. 1 part with wireframe, analysis with wireframe. 1 part with a sketch, analysis with a sketch. And it's I finished 30 seconds earlier. Okay, folks, let me see, where are you? Okay, are there any questions? So what I'm going to do is I'm going to stop this recording. I will leave the session. Close it basically, and I will come back with my 2-hour availability to you in the lab. There are also some GAs present. I don't know who they are, but anyway, we will be here for the remaining almost 2 hours to help you with any question that you have with the current homework problem, anything else. We're going to address it, but I will do that in the new session, because I noticed that when I stopped this thing and then I started again, there's now you will have to join. Okay, you will have to join to the new lab if you want to. And I don't have anything else to add. Okay, guys, see you in a few minutes. Okay, I've got to stop this and then go and make another.